Important, if I don't follow the chapter exactly as written, it's important that you take notes, because otherwise you aren't going to have a record of what I said, or, and the information might not even be in the book, And so try to take good notes. In fact, that was probably the number one thing that helped me improve my grades at UCLA, because when I transferred from Santa Barbara City College to UCLA, I went through the orientation. The orientation, they say, hey, your GPA is going to drop. For sure your GPA is going to drop. And I thought, no, that's not going to happen to me because I'm going to study extra hard and make sure my GPA doesn't drop, right? Well, sure enough, my GPA dropped. And I thought, and the thing was, I studied extra hard, and I thought, why wasn't I doing as well as I had done at Santa Barbara? And then it took me about a couple of quarters until I realized I changed a whole bunch of different things because I couldn't add more time. I was already studying, the maximum amount of time. I'm there at UCLA. I might as well take full advantage of it, spend all my free time studying. And basically, to make a long story short, the biggest difference was in how I took the notes and what I put in the notes. Because what happened was, when my first quarter at UCLA, I took this class. This class had a 1,000-page long book. And the 1,000-page long book, they're covering it in 10 weeks as a science class. And it takes, to read 10 pages of chemistry, I timed it once, and it took hours, because there were calculations you had to go through and whatever else. And if it takes let's say an hour or 2 hours to read 10 pages, how long is it going to take to read 1,000 pages? But, before I transferred to UCLA, I was learned by the book type person. And so I'd like to study from the book. The book is where you get your primary source of information. But I had to change that thinking. There was way too much stuff in that book, to learn. And so I had to be very selective. And the problem was I wasn't. I tried to learn everything in the chapter, and then I thought, I'm going to be, a good student that way. But what I should do is I should learn what the professor thinks is important. Well, how do you know what the professor thinks is important? Well, you got to take notes. And so I see a lot of students, especially in Chem 4, they don't bother taking notes. Either the memory is good, but memory fades. But during this period of time, I was learning about memory. Trying to think of study tips for studying and improving grades. They say that by the next day, you've already forgotten 60%. I forgot the exact numbers, but maybe psych or biology, neurology people can help me out there. But it was so true. So what I tried to do was, I couldn't write fast enough because I'm a slow writer. They say, when I was in high school, one of the teachers always told the entire class, I don't know how many times, 5, 10 times, to take shorthand. Because if you know shorthand, then you'll be successful in college. That's what he always said. I never bothered taking shorthand anymore. But I can't write that fast. But what I do is, right after class, I could remember some stuff, and so what I do is read through my notes and then fill in the blanks. It's too slow to write, but at least I remember it. But that memory fades quickly, so you have to do it right after class, otherwise it's gone. If I wait too long, then I've forgotten it. It's too late. I really like the courses where they allowed you to record. You can bring in a little recorder and record that. That way, I took a film class. There's history of French film there, and I could just record the lecture. She didn't mind. And that class was easy. It was an easy A because I knew everything she said, and I just wrote it down in my notes. And so before the test, I would just study my notes. I wouldn't crack open the books. There's too many pages of books to read. But the notes were more manageable. So you take a 1,000-page book, and then you have a stack of notes like this. The stack of notes, the thing is, you can go through that so many times. How many times can you read the book? Can you read a 1,000-page book 5 times? Some people say read it once before, read it after and then read it again and again. By the 5th time, you'll know it. But who has time to read a book 5 times? That was one of the study tips I saw as well. But can you read a set of notes? Yeah, I read a set of notes more than 5 times. I read my notes, every week I would review my notes. So when it came time for the final, I didn't have to study. It was already all memorized because I'd been reviewing it every single week, multiple times.
Do you mind if we take the audio with you?
No, I don't mind. You're welcome to do that. The question was, do I mind if you take audio? No. If you want to record this. So the point is that I'm not going to be covering, the book's material in exactly the same way the book is. And so what's better for the test? What's better is knowing how the book did it or knowing how I did it. Well, what's going to be better is knowing how I did it and what I think is important. Some of the stuff I'll not emphasize. And so that made the reading much more manageable. At UCLA, I never read the chapter before class. That meant I was confused during lecture, but that was okay because, the material's hard. Even if you read the chapter before, you're still going to be confused because the material's hard. And so, and the thing was at UCLA, the classes get harder and harder and harder. And so you just got to adapt to thinking you're not going to understand everything. Nobody does. And nobody in the class knows. It takes time to absorb it and then work through it mentally and then figure it out. But getting back to what you want to do is you want to make sure you know what's important, and that makes the reading much more manageable, because if you're reading a long chapter and the instructor said nothing about this topic, then just skim it, and then where the instructor talked about certain topics, then you dig into that deep. And so that way you can get through a 1,000-page book because you're skipping a lot of material and just kind of skimming through it. Well, anyway, getting back to this, Intro to Chemistry. Now, scientific method, what do scientists do? If you think about what does a scientist, what's the job? The job of a scientist, the job description of a scientist. I want to be a scientist.
Test a hypothesis.
Test a hypothesis. So if you're to say, okay, I want to be a scientist, I need to go out and test hypotheses. Is that it? Or
Try.
Do research, go into the lab, make a pot of coffee, that kind of stuff? Well, to me, when I think about scientists and what scientists do, scientists just observe nature. It could be testing hypotheses or doing whatever, but they're just observing nature. To me, like biologists will study living nature. Geologists will study rocks, minerals, that kind of stuff. Physicists will study forces, electricity, this kind of stuff. Well, chemists, what do chemists study? Chemists observe or study matter. So let's talk about matter. What is matter? Matter is the stuff that the universe is made of. It's what you and me are made of. It's what the table is made of. Matter is, well, how would you define matter? You could say, I guess, it's the stuff that everything's made out of. That's one way to define it. But do you know the more formal definition of matter? The more formal definition of matter is, this is the physical material of the universe. Well, physical material of the universe, well, the two constraints on the physical material of the universe. One, it takes up space. It takes up space, so there's a volume. to it. You know, it's not empty space. Is this room empty space mostly? No, you know, this room is kind of tricky. We don't consider this room empty space. This room is filled with objects here, but also this room is filled with, you can't see it, but it's filled with air. And so this is not empty space. What is empty space? A vacuum. A vacuum, if you sucked all the air out of here and left nothing, then that's the vacuum. Even though vacuum is not what we call matter, chemists study vacuums too. You know, the UCSB, there's one of the pioneers in vacuum technologies, Henry Weinberg, who tried to create ultra high vacuums on Earth. It's hard to do, you know, because sucking the air out is very, very difficult. But it takes space and it has mass. So space and mass. You know. How about light? You know, the light that's radiating out from the sun. We can see the sunlight. You know, at night it's dark. How about light? Is light matter by this definition? Does light take up space and have mass? Light, that's tricky. You know, how about the air in this room? Does the air in this room take up space? Yeah. And does it have mass? Yeah, you can actually feel it, you know, when you're riding a bicycle or whatever else. You feel the mass of the air there. But light does not. You know, light, and it's tricky because we'll talk more about physics later, but, you know, normally when we think about light, we don't think about mass. We don't think about space. You know, how big is light? You know, if I have sunlight, how much space does that take? Can I put it in a box? Give it to somebody? What size box will I need? You know, so something like that. Light is what we call transmission of energy, and it's technically not matter, and so we don't think of that. A vacuum. There are two things that are not matter. A vacuum, and it'd have to be a perfect vacuum because we could have a partial vacuum. You know, some people were thinking, you know, out in space. Out in space, they're going to get as perfect a vacuum as anywhere they can get, right? And so they wanted to build these silicon chips or silicon wafers out in space because on Earth, you know, contamination happens. You know, things get in there. If you just have a few atoms of contamination on a silicon wafer, that could lead to a defective chip because the chips are getting smaller and smaller. And so they have clean rooms where they suck out and filter out all the dust, but they also worry about other particles in the air that might contaminate these things. So they want to build things in a vacuum. If they build things in a vacuum, then there's very low risk of contamination. And if it's a perfect vacuum, then there's no risk of contamination because, or, you know, essentially, in theory, there would be no risk. And so it's funny because some guys proposed to grow silicon chips out in space by making an arm that protrudes out of the space shuttle, and then they can grow these chips out in space. Out in space, is there any air? No, there's no air. There's some contaminants, but maybe very little. You can't get that kind of vacuum on Earth. You can't get, because if you look at if you look at what's required, let me just show you. Getting a vacuum is not easy on Earth, and so let's look at. Hopefully, this works out. I wasn't thinking. This is the last minute here. What's going on with this? This is the kind of stuff you need. If you want to build a vacuum on Earth, you need these types of vacuum chambers. These are very thick walls. Some of them are like this thick. because gases can permeate through metal walls too, especially things like helium. You have helium atoms are. Do you guys know about atoms pretty much, or Well, as we think about like helium, it consists of these tiny, tiny particles called atoms, spherical. But those can, like the joints here, whatever else, there's all kinds of potential for gases leaking in. And so generating these huge vacuums, you have to build this thing like a submarine. It's horrendous. And then you get a little vacuum leak, and you spend weeks trying to fix it. Otherwise you can't get that vacuum that you want. And so vacuum is not matter. It's perfect vacuum and light. But even though vacuum and light are not thought of as matter, chemists still study those because they're going to have an impact. For example, on synthesis of silicon wafers, you need high vacuum to get high purity, and other things. And not only that, like sunlight. I mean, if there's no sunlight, the plants can't grow. We can't have photosynthesis. If there's no sunlight, we can't do lots of things. And so, go ahead.
You mean mass? You mean weight?
Okay, yeah, that's. The question was that when I talk about mass, am I talking about weight? Chemists use mass and weight interchangeably. Physicists don't. Physicists will cringe if I use mass and weight interchangeably. Do you know why?
What has to do with gravity?
Weight, yeah. Weight is, let's say, mass is just the amount of matter you have. And so, you're made up of atoms. So you're made up of these atoms. These atoms have a certain mass to them. And that doesn't change, but gravity can change. So, for example, on the moon, you're going to weigh a lot less, but your mass will be the same. And so normally when we think of mass, we think of kilograms or what? Pounds is weight. So normally when chemists think of, and physicists think of mass, they're thinking kilograms, grams, that kind of stuff. When we think in terms of pounds, we're talking about weight. And the reason why chemists use this interchangeably is this. If you're in a first floor lab and you go to the third floor lab, was there much change in the weight? Did the gravitational pull change significantly in going from a first floor lab to the third floor? No, the change is so small, it's hard to measure. I mean, it's negligible. And therefore, chemists think of it, it doesn't change much because we don't go to the moon. If the chemists did go to the moon, then they'd have to worry about it, right? Or maybe if you went from a first floor lab to a lab on top of Mount Everest, then maybe the gravitational pull is a little weaker at the top of Mount Everest, but not much. And so since the change is negligible, then we don't worry so much about it. Whereas physicists don't want to limit themselves from first floor to third floor. They want the whole universe, right? And therefore they'd cringe. And so chemists are a little different. And so this semester we'll be using these two terms interchangeably. When somebody asks you to get the mass of something, you just weigh it in the balance. If somebody asks you what the weight of it is, you can just tell them the mass in grams or kilograms. Okay. But typically this would be in grams or maybe kilograms. This would be in pounds. Okay, it turns out that these are not equivalent. But chemists will ignore that. And so there's a very easy conversion factor for this. There are 2.202 pounds for every kilogram. Is that right? Yeah. or 453.4 grams in a pound. And so almost 500 grams in a pound. This we don't have to necessarily memorize. This kind of stuff we don't. All right. Well, what is the physical material of the universe made of? The physical material of the universe is made of atoms. It's a little bit more than that, because there are things that are smaller than atoms. Do you know what could be smaller than atoms? Yeah, what we call subatomic particles. Subatomic particles are also matter, but we aren't going to worry about those just yet. And so when we're thinking about matter,
Should we cover the hypotheticals like antimatter and stuff?
Antimatter?
So that's more of the hypothesis.
Well, antimatter is a little bit more than hypotheses, because there have been, when you take matter and antimatter together, you get energy. That's taken. But we aren't. I mean, we would cover it a little bit in Chem 1B when we get to nuclear chem. Nuclear chem's if we get to nuclear chem, which we might, I'll have to take a look at the chapter again to see if antimatter's talked about. But we really aren't going to talk about it this time. All right. In fact, I'm going to define matter a little differently, because I'm just going to say matter is made up of atoms. For chemists, this is the way the chemists are thinking. And then the chemists are going to think a little differently than the biologists. So, for example, in biology, the scientific method is testing hypotheses. But, the chemists that I know don't think that way as far as the scientific method goes. So I'll do it. Okay, well, matter is made up of atoms. The chemists are going to study atoms. So atoms make up me, they make up this plastic, they make up all this stuff. That's what. Now, how many different types of atoms are there? A lot, There are a lot of different types. You look at the periodic table, many different types, but not that many, because if you think about, pretty much all the matter in the universe, it's right there. 100 and something, 100. Let's say 110 plus. A lot of those are actually synthesized. So this is the periodic table. This just lists all the different types of atoms that you see. So if you go, actually, maybe I should project it on the board. Easier to see.
Were you recording your lecture?
Yes.
Awesome.
Actually, I'm recording this, and I'll continue recording if there's interest in it. But I didn't do this for Chem 4 summer, but I'll do it for this. Well, here's a typical periodic table here. There's different types of atoms. These atoms, the different types of atoms, do you know what they call them? I mean, yeah, they have gases, a lot of these we see in nature, some of them we don't. Let's talk about this. We'll learn more about the periodic table as we go along. This is an interactive periodic table here. But some of these atoms were man-made, like this: rutherfordium, dubnium, seaborgium, etc. These were synthesized in a nuclear synthesis lab. A lot of these are naturally occurring, up to a certain point. naturally, which we'll talk about. These we say are radioactive. You know what radioactive means? Like if you have a radioactive atom, what does that imply? A radioactive atom is just unstable. That's all. And so some of these atoms have a very short life, but most of the atoms that we're going to be dealing with are stable. And so, looking at the different types of atoms, we have different names for those. So, for example, the first one would be the hydrogen atom here. So let's take a look at that. So what you want to do is you want to start to memorize what we call the name and symbol for this. And so the symbol for hydrogen is H. I think most of us already know. And then the name hydrogen. Okay. In addition to that, we want to get some kind of idea about the size. Is hydrogen a small atom or is it a big atom? What would your guess be? It's a small atom. What do you think? Is hydrogen the smallest atom? Just guessing. Or seems like it would be hydrogen. I mean, we're starting off the periodic table element number 1, which we call, let me back up there, but we call them elements. Hydrogen. These numbers here are the radius? Yeah. The radius here, 155. The units of this, the units that is at 155 microns, 155, is that 150? This happens to be 155 picometers. A picometer is extremely small. And so we got 155, well, where's hydrogen roughly? And so I'll show you hydrogen. Li, do you know what Li is? Li is lithium. And so let's take a look at hydrogen. Hydrogen is very small. Lithium was 153. Hydrogen is 53 picometers in radius. So 106 picometers, PM stands for picometer, in diameter. And so hydrogen is pretty small. So we just represent the atom as a little spherical ball like this. It's not a hard shell. When we think about these, it's not a hard shell. And we'll talk more about what exactly an atom is, but we represent the size of the atom. We just kind of circle like this. The atom, though, this is what we call the average size, because it depends on what it's interacting with or what we call bonded to. That can change the size. It can pull atoms in closer and make it more tightly bound so it appears to be smaller, or it might not hold on to it as tightly and it makes it appear a little bit bigger. And so the atom radius is not a hard shell. Okay, so this gets the symbol H. That's what we call hydrogen. Now later on, we're going to talk about something called isotopes. This is later, but let me talk about it now. Now, these hydrogen atoms in nature should all be identical. They're just little, 53 picometers in radius. And I'm just going to put about 53 picometers here because it's not fit. But later on, we'll learn that not all the hydrogen atoms are the same. Hydrogen atoms occur in water. There are 2 hydrogen atoms and 1 oxygen atom, therefore we call water H2O. And if we look at all the hydrogen atoms in water, they aren't all exactly the same. That is, there are some hydrogen atoms that are heavier than others. And we see that there are 3 different weights to this hydrogen atom, and it depends on what it's made up from. One of these weighs twice as much, and the other weighs 3 times as much as the other. And so there are heavier hydrogen atoms and lighter hydrogen atoms. These ones are much more rare. It turns out this third one is very rare. This third one, and thank goodness it's very rare because the third one's radioactive. This third one's called tritium. And fortunately, when you drink your water, you aren't going to drink much tritium. Otherwise, it would be not good for your health.
Do we usually synthesize it, or is it found naturally as well?
Tritium can be synthesized, but it can be found naturally in certain, but primarily synthesized. A lot of these radioactive elements are going to be man-made. You know, uranium's mined out of the ground, but the uranium mines are becoming depleted, and people are looking for alternative sources.
Is what is known as heavy water or something?
Yeah, exactly. You probably heard of heavy water. Heavy water is because, do you know all the water molecules here are not identical? There are a lot of water molecules in here. Water molecules are just these two hydrogen atoms and an oxygen atom linked together to form what we call a molecule. And there are heavier water molecules and lighter water molecules in here. And when you drink this, can you taste the difference between a heavy water molecule and a light water molecule? You can't taste the difference, nor can you see it chemically. But if you were to weigh the water molecules, they weigh different amounts. And that's how you can tell. You know? And it's very hard to separate the heavy water molecules from the lighter water molecules. You know, you'd need something like a very powerful centrifuge or some other thing. You know, nuclear chemists are into this kind of stuff because they want the heavier ones, right? So anyway, these are rare. Actually, when you drink water, it's mostly this one. You know, this is the relative mass. In fact, we have a unit. This is 1, 2, 3. U is called the atomic mass unit, and it's just about 1. This is about 2. This is about 3 atomic mass units. So if we weigh hydrogen, we call it roughly 1 U. We'll talk about where that number comes from later. All right, a picometer is just, again, very, very small. All right, what about helium? Is helium bigger or smaller? What would your guess be? Helium should be bigger or smaller? Helium's number 2. You would think it's bigger, but did you know helium's actually smaller than hydrogen? Let's see how much smaller. So let's take a look at this. So this one came up in let's see, physics. Why is the atomic radius of lighter hydrogen greater than? Look at that. Is that wrong? Yeah. Shouldn't helium have a greater radius? Helium's actually. They're saying it's heavier. It's true. Helium is heavier. You know, the relative masses of these, the relative mass of hydrogen's what we call 1 unit. Roughly, it's not exactly 1 unit, but roughly 1 unit. And then this what we call isotope. Isotope, we're going to talk about this later, but isotopes are the same element, that is, it's hydrogen, but different mass. Atoms of the same element, but different mass. And so this second one's called deuterium. They give it a special name. Those are heavier hydrogen atoms. We have the lighter ones. Helium, do you know what the relative mass of helium is, roughly? It's 4 units. And so, yeah, helium's heavier, more massive, therefore why isn't it bigger? You know, if it weighs more, shouldn't it be bigger? but it turns out it's smaller. Helium's is 31 picometers. So let's go to helium. What's the symbol for helium? He. It's about 31 picometers. Do you need to memorize these? No, you don't. But you do have to memorize this. You have to memorize the symbol and the name. And you have to make sure the spelling on the name's correct. The symbol for helium is He. Name is Helium, helium. And so that's interesting. All right, now what does a scientist do? Now, does a scientist say, okay, now I'm going to test my hypothesis? All right, so come up with a hypothesis for me. My thing is helium is smaller. What did you hypothesize? Did you hypothesize that? No, because didn't most of you predict it's going to be bigger? And so does a scientist do that? Shouldn't a scientist have predicted this hypothesis beforehand and then now test it? Isn't that what scientists do? Well, maybe now is the time we make the hypothesis. So did you have a hypothesis? Sorry.
Yeah, I was learning before that, like, as you go on, it's like the orbits, they pull in together. Something like that, like the electrons, they like have a pull.
Yeah. Yeah, that's a great hypothesis. How did you come up with that hypothesis?
I don't know, it's like, I remember I took chemistry, honors chemistry, so it's like a blur.
Okay. Yeah, so... Uh-huh.
I mean, the way I kind of see it is, you could take 5 strangers and put them in a room and they'd scatter.
Okay.
They'd have a radius of, say, like this.
Uh-huh.
Or you could take 10 people that know each other and put them in the same room and they'll all clump together.
Oh, there's some kind of...
So
some.
the group looks smaller, even though there's more people.
Okay.
Something like that.
Yeah, well, those are excellent. Those are excellent. And you know, I wouldn't have been able to come up with as good of hypotheses as you guys just did there, because to me, science is not done this way. You know, in science, you know, in biology, this is why I'm spending a little bit of extra time, and our book is a little different. Our book talks about the scientific method, of course, by testing hypotheses, because that's what people learn in biology. You propose a hypothesis and then you test it. Well, what's the hypothesis that you just proposed here? This is good. You know, this group of people. Did you guys hear it? That's an excellent hypothesis. A group of 10 strangers is going to take up more space. A group of 10 friends will cluster together because there's some kind of what we'll call attractive force, or you know, some kind of force bringing them together, right? And then the other thing about the electrons, if you know about electrons, you know, electrons are going to be attracted to electrons are negative. They're going to be attracted positive because opposites attract. And so that's another great hypothesis there, right? But in reality, you know, I have no idea. You know, in reality, when I think about science, you know, science to me is like this. Science to me is, we start off with not a hypothesis, we start off with an observation. And so this is just fact. You know, you can measure these things using instruments. You buy these fancy, expensive $100,000 instruments, you can measure these things. Right? And you measure these things, and then what we get are experimental measurements. Experimental measurements we call observations. This is a scientific method. To me, you know, I spent most of my time doing this in lab, as well as all my friends and colleagues. They do this. They take observations. And then from these observations that you take, you go, okay, I don't know what's going on there. You know, I got my observations here. Then what we do is we look for patterns. You know, patterns or trends. Or trends. And so we see, well, I kind of see a pattern here, right? This coming up. But you know, usually you want to take a lot of observations. So some of the observations you take look like this. You know? if we continue on, the gold, ignore the blue and the green for right now, and just look at the gold. Okay, after hydrogen and helium, element number 3, or the third type of atom that we're going to see, is lithium, Li. What's Be? Beryllium. And so what I want you to do is, actually I want you to memorize this. Can you memorize the first 4 symbols and names today? You know, the first 4 symbols and names. We'll just show you that. So we did hydrogen and helium. Then we have lithium. Lithium is Lithium, followed by beryllium. 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 2 L's. Beryllium. All right. Hydrogen. You've heard a lot about hydrogen, I assume, yeah? Helium, of course, everybody. Helium balloons. Lithium, yeah, lithium batteries. Beryllium, no, you have not heard much about beryllium. Actually, this area, the South Bay was heavily into aerospace, and beryllium. If you look at beryllium, do you see this yellow? This yellow we call a family, or a chemical family. And so beryllium is in the same family as magnesium. And you've probably heard of magnesium. Magnesium they use as metal for very lightweight applications, right? Well, beryllium is even lighter. You know, magnesium is about what we call 24 U, roughly. Uh-huh.
Sorry, do you guys think keys by any chance?
Did anybody find keys in the front?
Yeah,
In the front. Were you in the class right before this? No, nobody. Okay, sorry. So let me tell you one of the industrial applications of beryllium. One of the industrial applications of beryllium was in aerospace. And so for a while they were machining a lot of beryllium metal. But the problem was that all the machinists ended up dying prematurely. And it turns out that you don't hear much about beryllium because it's highly toxic. Why is it highly toxic? You know, we need magnesium, we need calcium for proper health. We don't want any beryllium. Even though beryllium's in the same chemical family, and you think, okay, beryllium, magnesium, calcium, it's all good, but it isn't all good. Do you know why beryllium is so toxic compared to, the reason why is because beryllium can substitute for magnesium and calcium in biological processes. Well, so what? If it substitutes, in geology we learned this, and there's no big deal. For example, if you have limestone, it's calcium carbonate. If you have marble, it's, calcium carbonate. If you have dolomite, it's magnesium carbonate. And so what's the big deal? Magnesium, calcium, it's all kind of the same kind of marble-esque look on your countertop, right? But can you come up with a hypothesis why beryllium is so toxic compared? And the reason why it's so toxic compared to the others is because of its size, its small size. Its small size makes it much more reactive. And so size does play a significant role in this, and so we're going to start off looking at sizes, even though sizes aren't even discussed in chapter 1. We'll take a look at that. But anyway, we look for patterns and trends, but we start off with observation. Too bad somebody didn't hypothesize the toxicity of beryllium before so many people end up dying from beryllium. You could read about it on the internet. But we get patterns and trends, and then if those patterns and trends are like, what should I say, pretty unambiguous, it's pretty consistent, pretty solid, then we might call it a law. And so, for example, like Newton, Newton, do you know Isaac Newton? Isaac Newton, this is why it confused me, because Isaac Newton doesn't have the K there. But, have you heard of Isaac Newton? Physicist came up with, if you're talking about gravity, was it Isaac Newton came up with gravity? Right. Because what he did was, did Isaac Newton hypothesize gravity first? What came first? The chicken or the egg? So did Isaac Newton hypothesize gravity and then started testing it with apples? Or did Isaac Newton observe apples dropping and then came up with gravity? What came first? Observation or the theory of gravity? Observations. Because what Isaac Newton noticed is there's a consistent pattern in how things drop. The time it takes, the speed, all these types of things. They're reproducible. And then he came up with certain laws. They're called Newton's laws of motion. Right? And that came from observation. It didn't come from him first proposing gravity and then deriving the laws of motion from gravity. Right? Because what happens is, from the laws, then we continue. We could stop here. Oftentimes we stop here because Newton's laws were enough to get people to the moon. You didn't have to know why. Why is there gravity, right? Or what are the inner workings of gravity? But sometimes people want to dig a little bit deeper, and so then they come up with a hypothesis. The way we define a hypothesis is like this. You have a law. The law is just some mathematical pattern. Usually, mathematical pattern. And so this pattern is reproducible, and this pattern can be modeled by a mathematical equation. This pen dropping or the apple dropping. And so we come up with a law, and it's a mathematical equation. This is what we call an empirical equation. Empirical equation. You know what empirical means? An empirical law, an empirical observation, an empirical equation. Empirical means based on observation. This equation did not come from some fancy theory. This equation just came from simply observing this and then just trying to model that mathematically. Empirical equation. And so empirical equation is based on observation. Okay, so we have an equation like this. Force equals mass times acceleration, or something like that, or whatever. We have an equation like that, but then you start thinking, about things, and you start thinking about, okay, why is this, or in other words, you want a more detailed or more fundamental description of what's happening. And so we get by a lot on just laws, but sometimes we try to dig deeper into things, and if we dig deeper into things, we might come up with a hypothesis. Now, a hypothesis, what this is a fundamental description, but it's what we call tentative. Because it doesn't have widespread acceptance. Now, I'm telling you, why do you believe me that the physical material of the universe is made up of atoms? I just told you it's made up of atoms. But you, as a scientist, you're going to say, well, what proof do you have that all matter is made up of atoms? Because can you see the atoms? Has anybody seen an atom? No. And so, what proof do I have that, it's this big, 53 picometers in radius? And so sometimes people will hypothesize. If I hypothesize that the matter of the universe is made up of atoms, that could be a tentative hypothesis because it doesn't have widespread acceptance. Now it has so much widespread acceptance that pretty much everybody's a believer. I don't think that, well, there could be some non-believers in atoms, right? But those are more on the fringe. And so right now, if I hypothesize atoms, actually, I ran out of room here, so let me go down here. It's no longer a hypothesis. When something has widespread acceptance, it's called a theory. And atomic theory is widespread acceptance. I mean, there's pretty much, in science, there's 0 non-believers in atoms. Everybody believes in atoms. Why? Because there's tons of proof. I mean, if you looked at the amount of proof for the existence of atoms, it's huge. Not only that, you can see atoms using instruments, manipulate single atoms. People have done it all the time. So nowadays, people accept it without proof, which you shouldn't do, because you're supposed to be these critical thinkers, and scientists are critical thinkers because this is how you, there's no answer key, right? In science, you can't. Well, let me check the answer book, right? There's no answer book. In science, the way science corrects itself or finds the right answers through critical analysis of this. And so, theory is widespread acceptance, widely accepted fundamental description. It's widely accepted fundamental description. But it has to do one more thing. It has to predict new, unforeseen results or observations. Ultimately, we'd like to get to theories because with the theory, there's less. But the theory can be quite complicated, and so let me give you an example of the scientific method. Scientific method would be an apple falling from a tree, right? Where did that lead? That led to this pattern laws, which led to Newton's laws, which led to the theory of gravity. Do you know what led to atoms? How long have atoms been hypothesized for? Since the 1700s. Did they have sophisticated $100,000 instruments then that could manipulate single atoms and observe? No. So how did you prove? If you were hypothesizing atoms in the 1700s, how could you have proved the existence of atoms at that time? In fact, how the heck did you even come up with that hypothesis that atoms make up matter in the 1700s? So let me just talk about that briefly with an example here. Okay, this example is going to be the development of atomic theory. Do you know what the observation was? The observation was like this. If you have a burning candle, let's say you have 10 grams of candle, and when you burn the candle, it goes to 5 grams, it goes to 2 grams, it goes to 1 gram, right? And so the candle gets smaller, and so it looks like the mass of the candle is shrinking and disappearing. But the thing is, if you burn a candle in an enclosed box, and you weigh the box before burning the candle, and you weigh the box after burning the candle, will the box weigh less after the candle is burned, or the same? The same. And what that means is that this, whenever we call that a chemical reaction, burning. When we have a chemical reaction, like burning a candle, the total mass, this is the total amount of matter. Mass is just a measure of how much matter we have. The total mass before is equal to the total mass after. And so you do the burning candle, you do a flash bulb, you do a whole bunch of stuff. You know, and what you do is you see a consistent pattern. This is a consistent pattern. In fact, there are no exceptions. We have different things. If there are a lot of exceptions in the pattern, then we don't call it a law. Do you know what we call it? If there are a lot of exceptions in the patterns, that is, the pattern works most of the time, but sometimes it fails, versus the pattern works all the time. In this case, the pattern works all the time. There are no exceptions that were observed. And therefore, we're going to call this a law. We call this the law of conservation of mass, or conservation of matter. Conservation of mass. Mass is the measure of the quantity of matter, so we can just extend this to matter. Matter is conserved. You know, it's neither disappears. Well, in a way, it did disappear because the candle disappeared. But it's still there because we still have the same mass. Now, if there are a lot of exceptions, we don't call it a law. If there are a lot of exceptions, we call it a rule. And so if we have a rule, then you can expect it not to be as consistent. Now, what was the hypothesis? Now, this might be a stretch for you, but the hypothesis was that matter consists of atoms. And so what happens in a chemical reaction is that the atoms get switched around. You know, you have the atoms that made up the candle, and those atoms that made up the candle get switched around to make, you know what happens when you burn a candle? You make CO2 and water. And there's some oxygen from the air, and that oxygen gets switched around to make the CO2 and water. And so the atoms just get rearranged. And so the hypothesis is that matter consists of atoms, and these atoms get rearranged in chemical reactions. And then we come up with a theory, which is atomic theory. Now, atomic theory, it didn't gain widespread acceptance until later. You know, there's still people saying that, you know, matter is infinitely divisible. You know, what's the smallest piece of copper you can have? Well, it's infinitely small because you can just keep cutting that piece of copper smaller and smaller and smaller infinitely. But you can't. Pretty soon you get the smallest piece of copper you can have is called the copper atom, because if you try to break up the copper atom into smaller pieces, it's no longer copper. And so the other hypothesis that was going around was infinitely divisible. And what kind of sealed this, the atomic theory, is that it predicted something. Atomic theory predicted something that it could kind of test. And what it predicted was a law. Atomic theory predicted the law of multiple proportions. The law of multiple proportions just predicted this. It predicted that when you arrange atoms together, they're going to occur in, jumping ahead, but when we arrange them and bond them together, we get simple whole number ratios. For example, hydrogen and oxygen can combine to make water, H2O, hydrogen and oxygen can combine to make hydrogen peroxide, H2O2. But what you wouldn't see is this. The law of multiple proportions won't say you can have 2.1 hydrogens and 1.5 oxygens. You know, if you had infinitely divisible, then you should be able to have any amount you want, right? And so if I want a little bit more oxygen in my water, give it to me. Give me a little bit more oxygen in my water. Can you put a little bit more oxygen in your water? Not the gas that we breathe. Maybe that's a bad example. Can you put a little bit more hydrogen in your water? I'm on a low oxygen diet? No? No, it's not possible. It's the law of multiple proportions. So we don't want it. Did you hear the joke? I know this joke. The joke of the hydrogen peroxide joke? No. Okay, maybe this delivery is not going to be so good. But there's two people that go into a bar. One person says, I'll have a water. The other person says, I'll have an H2O2. And I'm dying. Well, anyway, that's it. That clock screwed me up. Sorry. We're going to continue chapter 1 tomorrow.